Hello. In this video, we're going to take a look at constant acceleration. We'll take a look at it from what it means to any associated variables and units, the equations involved, and of course, we'll even do some examples as well. Remember to pause or rewind the video as needed. Let's begin. Acceleration overall can be defined as a change in velocity over time. Now, I'm going to start with an equation before I get into what the variables are. The equation for it is A, which stands for acceleration, equals a change in velocity, delta. The triangle means delta, that means change in velocity. So delta V means change in velocity over time. Now, you always write a change in something as a final value minus an initial value. So I'm going to rewrite this delta V as V minus V naught over T. Okay, so now let's kind of explain what this means. I'm going to rewrite it one more time. So A equals V minus V naught over T. Okay, let's describe what these variables are. A stands for acceleration. Now, it's constant acceleration, so what that means is you are going to constantly increase or decrease your rate of velocity. In other words, you'll speed up or slow down at the same rate. Your V in the equation stands for the final velocity. Now, the final velocity is the second velocity mentioned in the problem. When you see V sub 0, that means that's always going to be pronounced as V naught, V naught. And what it stands for, ladies and gentlemen, is the initial velocity in the problem. It's the starting velocity, also in meters per second. So whatever the first velocity list, that's V naught. Whatever the second velocity that the problem mentions, that's V final. And then, of course, T is time. And time is still in seconds. Let's take a look at a couple examples here to apply this. Number one, a car starts from rest and reaches a speed of 40 meters per second in 8 seconds. What is the acceleration? Whenever you see the phrase starts from rest, you automatically need to equate that to V naught equals 0. Starting from rest means you start with no initial velocity. Therefore, V naught equals 0. Now, V naught equals 0, that means the other speed, and we know it's speed because velocity or speed have units of meters per second. The other velocity and speed in the problem must be V final. Seconds goes with time, and we're looking for acceleration. So we annotate the problem twice. We annotate it in the question, and then we make a nice vertical list of variables, starting with the unknown. A is the question mark. V is 40, V naught is 0, and T is 8 seconds. The equation we want to use is right here. Let's write it down. A equals V minus V naught over T. Now, since V naught equals 0, let's go ahead and zero out that part of the equation and substitute into what's left. A equals V over T, therefore V is 40 meters per second over 8 seconds, and we get 5 meters per second squared. Now, since the answer is positive 5, what that tells you, ladies and gentlemen, is that the object is increasing, this car is increasing its rate of velocity, it's speeding up, it's increasing its velocity 5 meters per second every second. So the first 0 would be the initial speed. After 1 second, it would be 5. After 2 seconds, it would be 10. After 3 seconds, it would be 15, and so on. It's increasing its velocity by 5 meters per second every second. So we can say, since it's positive, this car is speeding up going forward. Number 2, a plane lands and slows from 80 meters per second to 20 meters per second in 4 seconds. What is the acceleration? The first velocity listed should be V naught. Second one listed should be v final. Time, acceleration is the question mark. So again, make a nice vertical list of variables. A is the question mark. V is 20. V naught is 80. T is 4. Acceleration equals final velocity minus initial velocity over time. Plug right into it. 20 meters per second minus 80 meters per second over 4 seconds. So that would be negative 60 meters per second over 4 seconds, which is negative 15 meters per second squared. Now, because the answer is negative, what that means is this airplane is slowing down by 15 meters per second every second. The airplane is slowing down going forward. Now, another way to have negative acceleration would be to speed up going backward or speed up going in a negative direction. That's clearly not happening here because the plane is going forward as it lands. So if it's going forward, it must be slowing down in the process. Now let's take a look at 4 equations that can be used to model constant acceleration. Before we do, pause the video and copy the chart that you see on my screen. It has 6 columns by 5 rows. Resume the video when you have your table constructed. Okay, now that you have your table put together, let's fill it out. In the top column, we're going to write equation. Our formula, our equation, is going to go in the first box. The next 5 boxes will be the variables involved in these 4 equations. The first one's going to be x. The second one's going to be v. The third one is going to be v naught. The fourth one is going to be a. And the fifth one is going to be t. Before we begin, just a reminder, let us review what these variables stand for. X is the final position of the object. It's how far the object ended up in the problem. It has a unit of meters, and if we're looking for this in a problem, the problem would be asking how far. V is the final or second velocity listed in the problem in meters per second. And in a problem, that would be, of course, how fast something is going. V naught, if you guys recall, is the initial. Initial means starting or beginning velocity. Also in meters per second. Also kind of referring to how fast an object is going. T stands for time. Time is in seconds, and you would see the problem asking for time if it asked how long it took for something to do something. Okay, and finally, you have A, which stands for acceleration. Now, acceleration's pretty straightforward. They don't ask you how far, how fast, how long when it comes to acceleration. They just simply ask you for the acceleration. And then it has the strange unit of meters per second squared. Okay, let's fill out this table so that we can make some sense out of the equations that get used. The first equation that we're going to list, and I'm going to list them by number and refer to them that way. I'm going to call this equation 1, equation 2, equation 3, and equation 4. Now, equation 1 can be summarized as V equals V naught plus A times T. Now, what we're going to do over to the right is we're going to check off the variables that are in the equation, and we're going to X out the variables that are not. Every equation is always going to have 4 variables present. 1 variable will not be there. So in black, let's check them off. So We have v final. You can see it right here. We have v naught, initial velocity. We have acceleration. And we have time. So clearly, the one variable we do not have in this equation is final position. So if the question is asking you how far and you're looking for final position, it should be clear to you that you're not going to use that equation. Second equation is x equals v naught times t plus 1/2 a times t squared. Now, checking off our variables, clearly there's an x in the variable in the equation. There is a v naught, there is a, and t shows up twice. What we do not have is final velocity. Equation number 3 is going to be written as x equals, let's zoom in on this, v plus v naught over 2. This would be initial plus final velocity over 2. That's essentially average velocity times time. So average velocity times time is another way to describe constant acceleration. However, this is a way to describe constant acceleration with final position x, final and initial velocity v, time, but no acceleration. So this is the equation you would use when you do not have acceleration. And our fourth and final equation is going to be written as v squared equals v naught squared plus 2ax. You can see that x is in the equation, v and v naught are in the equation, as is acceleration a. However, this is the equation you would do. Notice the variable time, t, is not present. So we use this to help us figure out which equation to use. We make a good vertical list of variables, and if I have v, v naught, a, and t, then I would choose equation number 1. If I had x, v naught, a, and t, I would choose equation 2. If I have x, v, v naught, and t, and I do not have acceleration a, I would choose equation number 3. If I have v, v naught, a, and x, but no time, then I would choose equation number 4. Let's take a look at some examples. Again, we're going to refer to the equation by numbers. A car starts from rest and accelerates to 30 meters per second while covering a distance of 60 meters. Part A, what is the acceleration of the car? Part B, how much time did it take to travel the 60 meters? Okay, so first things first, let's annotate the question, then we'll make a nice list of variables on the side, then we will accomplish part A and part B. So when we see the phrase starts from rest, remember, ladies and gentlemen, that means v naught equals 0. That means this other speed is v final, a distance of 60 meters, so that would be x. We're using x now instead of d. So we want to list x, v, and v naught. So x is 60 meters, v is 30 meters per second, and v naught is 0. Now for part A, acceleration is the question mark, and for part B, time is the question mark. So I am looking for an equation that has x, v, v naught, and a, but not time. Well, the only equation that does not have time in it is number 4, no time. So we're going to write down equation number 4 for part A. V squared equals v naught squared plus 2ax. Kind of looks like a long equation, but what you have to remember to do is if you use anything that is equal to 0, cancel that part of the equation. So v naught squared would be 0 squared, so I could cancel that. I'm going to put an arrow with a 0 through it, and it gets rid of that part of the equation. This now becomes v squared equals 2ax. Much smaller, much easier to work with. Well, ladies and gentlemen, if I'm trying to solve for a, then I've got to get rid of the 2 and the x. So I can divide by 2 and I can divide by x simultaneously. 2 cancels, x cancels, a is now by itself. So for part A becomes v squared over 2x. Plug in our numbers. V was 30 squared over 2 times 60. Now 30 squared is 900 over 2 times 60 is 120. I'm going to go ahead and pause the video, try and plug that in your calculator yourself. Okay, let's see what you got. We should have gotten an acceleration of about 7.5 meters per second squared. Now, in part B, we were looking for time. But keep in mind, we now know the acceleration is 7.5 meters per second squared. So I could literally choose any of the 3 variables here that all have acceleration in them, because now I know everything. I know everything except for time. Okay, so I'm just going to go ahead and choose the first equation right there. V equals V naught plus A times T. Again, we will cancel V naught just like we did in the previous part, and the equation reduces itself to V equals A times T. Remember, ladies and gentlemen, you're solving for T this time, so we have to divide by A. If we do that, we get time is equal to final velocity divided by acceleration, and it's 30 meters per second over 7.5 meters per second squared. When we divide those two, you should end up with about 4 seconds. It takes 4 seconds for the car to travel that far. On to number 2. It says a ball is dropped from rest. So just as we see the phrase starts from rest, whenever you see the word dropped, when all dropped objects start with no initial velocity. So that's another one we want to see. When we see starts from rest, initial velocity is 0. When we see dropped, initial velocity is also 0. Now, we are taking a look at something that is called free fall acceleration. Free fall acceleration due to gravity, because when we drop it, gravity will make this fall. We have a special acceleration for this one. Acceleration is equal to a negative 10 meters per second squared. Okay, this is called the free fall acceleration due to gravity.
Now we're ready to proceed and make a list of variables. The question wants to know what is the initial speed? Well, first of all, let's list all 5 variables so we know what's known and what's not known. How high the ball goes, we don't know how high it goes, so y is a question mark, right? But that's actually part B. We'll get to that. Okay, we know that the velocity at the top is 0. That's the velocity at the top, the final velocity is, and what we're doing is we're just focusing on the blue section right here, where this is the initial velocity we're looking for, and this is the final velocity at the top right here. Okay, that means the initial velocity is the unknown, that's what we're looking for, and we have A is equal to negative 10 meters per second squared. Remember, that's a constant acceleration due to gravity. And then t, if you remember, is 2 seconds, not 4 seconds. The total hang time is 4 seconds. We have to cut it in half, so we just focus on t1 being only 2 seconds. Now, with this right here, we can work with this, and this. And we can use equation number 1 because we have v naught, a, and t because we're looking for v naught. Okay, so for part A, we have v equals v naught plus a times t. We know the final velocity at the top is 0. So if we write this, we get 0 is equal to v naught plus a t. Now, in order to look for v naught, let's go ahead and subtract a times t over to the left. And now v naught is by itself. V naught is equal to negative a times t. But v naught is going to be equal to negative. Remember, a itself is also negative. So negative 10 meters per second squared times the 2 seconds. Notice that will cancel. And v naught is equal to 20 meters per second. So it was hit, excuse me, the ball was kicked at 20 meters per second off the player's foot. Okay. And then for part B, we want to know how high it goes. What was the highest point? Okay, now we could use equation 3 like we did last time. Okay, which is y is equal to v plus v naught over 2 times t. Velocity at the top is 0. And so we get v naught times t over 2. That's all that's left. That would be 20 times 2 divided by 2. And you can see those 2's cancel, and it's a very easy 20 meters high. Okay, but just to show you, ladies and gentlemen, you could have chosen another way. So what if we had chosen equation number 2? Y equals v naught t plus 1/2 a t squared. Same idea, you just have more to plug in. So 20 times 2, that's the v naught t, plus 1/2 times negative 10 times 2 squared. That's the 1/2 at squared. That would be 40 plus a negative is minus. Now, what do we have here? 4, 2 squared is 4, times 5, that'd be 20, and 40 minus 20 is 20 meters high. So you have alternates. You have alternative solutions. When you have enough variables to choose from, because once we find out that this is 20 meters per second, right here for v naught, then it becomes any formula that has y in it is what we're going to choose. Because remember, x and y get treated as the same letter. So next to this one, I'm going to say x or y, either of those two. Okay, I hope you found this helpful. Again, remember to pause or rewind the video as necessary. Again, ladies and gentlemen, do not do the next page on multi-problem steps. Go ahead and skip that. Graphing notes. Go ahead and skip that. The example 1 that has the graphing question on there, skip that. And then finally, example 2, which also has a graphing question, skip that. So we're going to skip these last 4 remaining pages. And once you're completed with this, go ahead and submit your notes. Okay, so let's make a list of these variables. For part A, well, first of all, we know that the object is falling 30 meters. So instead of x, we're going to write y, because y is a vertical variable of displacement, and x is a horizontal one. So how far you went in the x direction is x, how far you went in the y direction is y. And since you fall 30, that's the same thing as negative 30, because we went downward in the downward direction. So negative 30 meters is going to be our displacement, our final position rather. How long? Well, that would be time. Now our final velocity, we don't know how fast it's going to be going, but if you look here, how fast it's going to be going when it has fallen, that's actually part B. That's what we're going to be trying to find in part B. V naught is 0 because all dropped objects start from rest. The time we don't know, and the acceleration is this free fall acceleration due to gravity, or the negative 10 meters per second squared. T is what we're looking for part A. So looking at our equations, we have y, we have v naught, we have a, and we're looking for t. Okay, using those, this equation here that has displacement, remember, x and y can be used interchangeably, right? So we have y instead of x, we have v naught, a is negative g, which is negative 10 meters per second squared, and we're looking for time. So we're going to be using equation number 2 here to do example number 2. So part A, we're going to start by writing the equation down. So y is equal to v naught times t plus 1/2 times a times t squared. Now remember what we talked about before. If you have a variable that is going to cancel part of your equation, then go ahead and reduce the look of the equation. So for instance, if v naught is 0 and 0 times time is 0, then this whole middle term here goes away. And the equation reduces itself to y is equal to 1/2 a times t squared. Now, we're going to solve for t, but it's going to take us 3 steps to do it. So let me write it again. Y equals 1/2 a t squared. In order to solve for t, you have to get rid of 3 things. You have to get rid of the half, the a, and the squared. So for starters, I'm going to multiply by 2 so I can get rid of the half. If I do that and I rewrite this, I get 2y equals a times t squared. Then I'm going to divide by a, because that gets the t squared by itself. Then I get 2y over a equals t squared. Finally, I'm going to square root because that's the opposite of squaring. And when I do that, I get t equals the square root of 2y over a. Plugging into that, it's 2 times negative 30 over negative 10. You guys can see that the negatives will cancel, leaving you positive. And we're going 2 times 30 is 60, divided by 10 is 6. And the square root of 6, the square root of 6 is approximately 2.5, about 2.5 seconds that it takes to fall. Okay, now part B is asking how fast it's going to take. So we already know the time it's going to take. The time is now 2.5 seconds. So if I know this, and I know this, and I know this, and I'm looking for the speed, how fast it's going to be going, or the velocity, how fast it's going to be going after 2.5 seconds, now I can come back to equation number 1. I'm looking for how fast it's going. The initial speed is 0 because it's dropped. The acceleration is negative 10, and the time we just found to be 2.5 seconds. So I'm going to now use equation number 1. V equals V naught plus a times t. Again, cancel the 0 because the object was dropped. And this becomes V equals a times t, and we're simply plugging into that. V is equal to negative 10 times 2.5, and we get negative 25 meters per second. Now, since the question was going how fast is speed? Okay, so all we need is just the numerical part, and we can say, or 25 meters per second. Okay, the negative, so you understand, means the downward direction. So if we're talking about the velocity, it would be 25 meters per second going downward. But since the question only asked how fast, then we're okay answering with just the 25 meters per second. Number 3. A car traveling east slows from 30 meters per second to 20 meters per second in 4 seconds. A, what is the acceleration of the car? B, what is the car's displacement over the 4-second time interval? Well, first, on a map, pretty good to know, north, south, east, and west, meaning positive, positive, negative, negative, just like a number line. Okay, so positive direction going east is positive. Now, since you have 2 velocities here, the first one would be v naught, the second one would be v final, the third would be the time, and we're looking for acceleration. Making a list of our stuff, we know We do not know x. The car's displacement over the fourth time interval, that will be our x. So x is a question mark, but that's part B. V is 20 meters per second. V naught is 30 meters per second. Acceleration is what we're looking for, and t is 4 seconds. So based upon what we're looking at here, v, v naught, a, and t, we're going to be using, again, that first equation there, v, v naught, a, and t. V equals, this is for part A, v equals v naught plus a times t. Now, in order to solve for a, you need to get rid of the v naught and the t. So starting with the v naught, we can go ahead and subtract v naught both sides like this. And when we rewrite this, we get v minus v naught equals a times t. Then to get a by itself, we're simply going to divide by t. And that equation should look familiar to you. V minus v naught over t, well, that was an equation that we used to describe acceleration. Right here. Now we can go ahead and plug in. 20 minus 30 over 4. Which would be negative 10 over 4, which would be negative 2.5 meters per second squared. So what that answer means is the car is slowing down going forward, but it's slowing down at a rate of 2.5 meters per second every second. Oops, let me highlight that. And then part B, looking for the car's displacement, there's a variety of equations we could use to find x. We could use the second equation for x, since we have initial velocity, time, and acceleration. Or we could use this one here. Equation number 3 is actually a very easy equation to use when we're looking for displacement. So we'll try equation number 3. X is equal to v plus v naught over 2 times t. Plug into it. Final velocity was 20 plus 30 over 2 times 4 seconds. Which the average of 20 and 30 would, of course, be 25. And 25 times 4 would be 100 meters. So this car, in the process of slowing down, took 100 meters to slow down from 30 meters per second to 40 meters per second in that 4-second time interval. And in the last example here, number 4, we have a ball that's punted straight upwards. Its hang time is 4 seconds. What was its initial speed, and how high was it at its highest point? So a couple of things that we should know. Hang time equals total time in the air. Okay, another thing we should know is if we take this, look at a picture, the ball is going to go straight up and then straight down. So we could divide this into 2 sections. There's the part that's going up, which we'll call T1, time going up. And then there's T2, which is this other part going down, time 2. And T1 going up equals T2. In other words, time up equals time down. Okay. Now, if the total time was 4 seconds, that means T1 equals T2 equals 2 seconds. We have to cut that in half. Another thing we should know is that in order to change direction here, the velocity at the top has to equal 0. So let's make a note of that. velocity at the top equals 0.